So here is the key idea, and that distinguishes everything the way we're doing it, because we're going to do it in this abstract notation from the book. And we start with the idea that d squared dx squared is Hermitian. And its eigenvectors are sine nx and cosine mx. I'm going to use n and m just to distinguish between the sine and the cosine. We also have just seen that minus I d by dx is Hermitian with eigenvalues e to the I kx, is what we'll tend to call it. We can now use these as basis vectors. What happens? Well, first of all, we know a whole bunch of stuff are orthogonal. Let's just suppose we're going from minus pi x to pi, which is a nice interval to use with the sine and the cosine. So the integral from minus pi to pi of sine nx cosine mx dx is 0. The integral from minus pi to pi of sine nx sine mx dx is, well, I have to be a little careful. It's 0 if m is not equal to n. And because we're doing minus pi to pi, we get 1 over pi if n is equal to m. And then the only other, and that's the same if I stick cosine in here. And that's what it means to be orthogonal. And you can check these integrals out, do them in Mathematica. You can look up in the book. The book actually derives these facts, because this is the heart of the Fourier transform in the Fourier series. And now, having established that, we can use our Bronquet notation and do all of Fourier series and Fourier transforms in one piece. If I'm going on a finite interval that's periodic, I'm going to be doing Fourier series. If I'm going on an infinite interval, minus infinity, infinity, I'm going to be doing a Fourier transform. I can. Now, what does this look like? Well, I will take f of x. I'm going to think of it as a vector. So I can write it as a sum from n equals 0 to infinity of some coefficient a sub n times my sine basis vector plus some b of n times my cosine basis vector. Or I could write it as a sum from n equals minus infinity to infinity times some coefficient times my exponential basis vector. I now know how to find all those coefficients. Why do I know how to find all those coefficients? What do I do? If I have a series in terms of kets and I want to find any of these coefficients, what do I do with this vector? I use a inner product or a projection. It's that simple. So I would just have n from the sine basis projected with f is a sub n. And using the cosine basis with f is b sub n. And n using the exponential basis is c sub n. And I'm done. I've just taught you everything you need to know to do a Fourier series, because these inner products are just integrals. And these kets are just functions, and that's just a series. That is a Fourier series. We are now done with Fourier series. In 30 seconds, I will teach you how to do a Fourier transform. Our basis vector k is e to the I kx. But now k is a real number. If I want to write f of x, and I want to sum over all real numbers, how do I sum over all real numbers? I integrate. It's that simple. That's why it's a big S, because it stands for sum. And I sum the coefficient times the basis vector. So this is my a sub k's that are being summed over, and this is telling me to sum over all k, and this is my ket k. So this is exactly this. And instead of a subscript, I use a function form because I'm going over all k, all real numbers, so it's become a function. And just to give myself a little more room, And now, to find the coefficient, how do I find a coefficient? I do what? I just do the inner product of k with f of x. And just to write it out for you so you can see it, an inner product is what? An integral. And a bra has a what? Complex conjugate. So it's e to the minus ikx f of x dx. And this is why in Fourier transforms, which you may not have done yet, but one of the confusing things is to keep track of whether that's plus and that's minus or the other way. If your basis vectors are e to the minus ikx's, your coefficients are e to the ikx's, because they're a projection, and projection takes the complex conjugate. So this one page has everything we've done for the last 2 weeks, done in really cool notation, and you've just learned everything you need to know about Fourier series and Fourier transforms. Now we'll spend all of tomorrow and Thursday digesting what this means. But I wanted it in one short lecture so you could go back to it as a coherent piece, these two lists, and stare at them until they make sense.
The exam on Thursday?
No, a week from Thursday is the next exam, because this will be on your next exam. All the linear vector space stuff will be together, including this. We'll see you tomorrow, where this will all make sense.